There we go. Hi, everyone, and welcome to the first webinar of the 2024-2025 NAGT webinar series season. I'm Ashley, they, them, and I'll be your NAGT support person for today. And our webinar today is entitled Using Geophysics Field Instruments to Engage Students in Societal Applications and Geoscience Career Skills. And Sarah, Andy, and Beth will give us an overview of existing teaching resources and the process for instrument loans from the EarthScope Consortium. But first, we do have a few things that we need to go over. First, the NAGT webinar series is a one-stop shop for increasing our community's capacity in Earth education. Webinars in our series feature novel and innovative work such as Earth education, research and pedagogy, new teaching materials, and the classroom experiences of, the classroom and professional experiences of people just like you. The NAGT webinar series is free and open to the public. We often get questions about whether it's okay to invite your colleagues. Yes, it is. Please invite them. We'd love to have them. And throughout the webinar, please feel free to use the chat box as a place for discussion, questions, and comments. Additionally, you feel free to use the reactions tab if you'd like. Otherwise, in terms of interacting with one another, please remember that we do still follow the NAGT Code of Conduct, even in webinars. I'll drop that in the chat for you to review as you please. And with that, I'll go ahead and turn it over to you, Beth.
Awesome, thank you. Let me share my screen. All right. Okay, well, as Ashley said, this is using geophysics field instruments to engage students. I am Beth Pratt-Situla with EarthScope. Before we launch into the main part of the webinar, I just thought I would give you a little background on the projects that have come together to bring us these teaching resources and the opportunities to use instruments. So there's a project called GETSI, which is Geodesy Tools for Societal Issues, that was started by UNAVCO and supported, by community members, collaborators. There was the Iguana project started by Iris, which also has been deeply working with community partners. And these are being brought together into what we're now calling the next phase of GETSI, which would be geophysics tools for societal issues. So I really wanted to highlight how this has been very collaborative and very oriented in making sure that this addresses a wide range of the community. And both CERC and NAGT have been partners in this. A little bit on the EarthScope Consortium, which is now a combination, a merger of IRIS and UNAVCO. We run, now that we've joined since the beginning of last year into EarthScope, we run both geophysical facilities for the National Science Foundation, both the seismic and the geodetic one. As mentioned by Ashley, we are very wanting, even though we can't be out in the field with you today, we want to encourage a lot of interaction. So please use the chat box, and there will be time later in the program where you could unmute and ask more complicated questions if needed. But we, the leaders, will be monitoring the chat and may be able to answer some questions in time, or break for questions that are pertinent to the moment. So a little overview of what we're going to do, why use geophysics instrumentation and data, like what's great about it, an overview of the existing resources and modules and the methods that they entail, how to borrow instruments if you're interested in doing the instrumental part yourself with any range of students, and you'll have some time to explore the resources and have discussion and questions near the end. But before we launch into our part of the program, we did just want to get a little insight into the spectrum of backgrounds that you all represent. So if you could launch the poll questions, Ashley. Okay, so are these showing up for people? I'm a leader, so I can't tell. So anyone let us know if they're not showing up.
Yes, I'm getting responses.
They're showing up. Okay, great, awesome. So we'll give people just a couple minutes and then we'll sort of show the results that we have gotten. All right, I am seeing that the poll numbers have slowed down quite a bit, so we'll give it like 10 more seconds, and then I'll end the poll and we'll flash up the results. All righty. Results. Okay. So let's see. We have half of people are saying that they, are do introductory geophysics, and then we have certainly, a blip of extra people in the geophysics realm and environmental science, but there's really quite a good spectrum showing, I think, that there is ways to do geophysics in a, people are interested from across the spectrum, and we would say there are ways to integrate these methods into this whole range of teaching. So the different levels that people are specifically planning to teach with the geophysics, there are a little bit more at the majors level, but a really solid number of people, both in majors and non-majors introductory science. And a few people have added things into the chat. You can scan those on engineering, geography, physics. Those are all great ways to use geophysics as a way to learn aspects of those topics as well. And there's a solid middle of the road as far as people's experience with geophysics. Most all of you are in the, I know a bit about it, or I have a little experience, and just a fewer people on the know and the very experienced level. So feel free, if you're on the more experienced level, to give your own input, and no question is an unreasonable question if you know nothing about it. So please feel free to engage at all levels here. I am gonna stop sharing here, and I am going to give this over to Andy.
Thanks, Beth. So I'll introduce things for the project goals of the GETSI and Iguana project. So our main mission is to increase the number of students in geophysics. And in particular, we want to attract a diverse population of students. The next goal was to develop inclusive curriculum materials with the objective of highlighting applications of geophysical tools and methods. We really wanted to focus on societally relevant themes, and in the next slide, I'll justify why that is. And finally, we want to include applications to environmental problems in urban settings when possible, and that's going to be related to the focus on societally relevant themes. So next slide, please.
Oh, there. Okay.
So I mentioned this in the previous slide in the idea of inclusive coursework. And so what is this and why is it important? So inclusive coursework is designed to highlight the appeal of geoscience majors, so not just geology, but the broad range of geoscience majors, through societally relevant themes. And the point there is that students are going to be more engaged if it's something that they care about. So societally relevant themes are designed to highlight that. The inclusive coursework also has to have some kind of engaging structure and format and content. So it's something that's more than just getting the information and equations out there, right? But it's actually something that's going to be engaging and something that people want to learn about. The students want to learn about, and designed for a variety of skill levels. Just recognizing that any classroom that we stand in front of is going to have students that are much more capable and less capable, and that our exercises should be able to have something for everybody in that context. Inclusive coursework includes varied, early, and frequent assessment, and this is really important to allow instructors to make changes to how they're delivering courses responsive to how students are performing in the class, and responding to the material that's being provided. And finally, inclusive coursework, the content of inclusive coursework shows how practitioners from a range of backgrounds have a place in the discipline. So this is, even looking forward towards careers. So if we can demonstrate to students that they care about the science that they're learning about, and then we can also show them that there's a possibility for a career in this in the future, there's the highest level of probability that they might actually decide to become majors and actually become, achieve our goal of attracting more students to geoscience. Next slide, please. So why is it important? What is the point of trying to engage a broader range of students of the population if we're unwilling to consider the perspectives, needs, and motivations of the students? So this brings up some interesting elements of why geoscience is attractive to some of us, but may not already be attractive to students from a broader background. So for example, there's a lot of field-oriented and outdoorsy perceptions of geoscience majors or people who participate in geoscience that might actually discourage participation because not everybody likes to go outside and get lost in the woods. Second, urban areas have a lot of potential students, but they lack access to natural areas. So even if those students are, interested in getting lost in the woods, it might not be possible to do during the course of coursework. And then finally, it's an opportunity to leverage research-based pedagogy. We know a lot about how people learn, and we can use that in order to engage a broader range of learning styles that might be, reflected in a broader range of the population that we're trying to expose. Next slide, please. So why do we focus on curriculum? So we want to achieve diversity, equity, inclusion, but that requires systematic change. Our educational system is obviously a system, and so to transform it, we need to look at it as a system and apply new approaches to address the inequities. So curricular materials are a critical component of the educational system, and so we're looking to change from that sort of part of the foundation. Second of all, we focus on curriculum because of the attract, support, and prepare framework that was highlighted by John McDarris in his 2019 paper, cited at the bottom of the slide here. And the idea is that curricular materials can either attract, support, and prepare students, or they could fail to attract or repel students or fail to prepare students. And so we need to design the coursework in a way that it's positive, attracting, supporting, and preparing students for the next stages of their education. Next slide, please. So the last thing I'll say on this before we move on is a little bit about the barriers to inclusion that we were thinking of when we were designing these modules. So for example, there's certainly a lack of knowledge and some misconceptions about geosciences, geophysics in particular, partially because of lack of exposure in high school or grade school for some students. There simply may not be space in a state-mandated curriculum to have a geology class in high school. And so we're trying to overcome that as these students move into college and they don't have any exposure. So this is a way to sort of be as engaging as possible and make up a little bit of that lost time potentially. There may also be some cultural barriers. For example, family of students may perceive that professional training like medical doctorates or law degrees or engineering degrees are preferred because they have very clear paths to careers. Well, we want to also highlight that there are good opportunities for careers in geoscience. And so we try to link the curricular materials with that element as well. And finally, that there are career aspects attractive to privileged students that may not actually be desirable to students from historically marginalized groups. And again, back to the example of, well, some of us like to get lost in the woods just because that's how we grew up, but that's not how everybody grew up. And that actually might be a detriment to attracting those students. So to show students that there are other ways to engage in geoscience and geophysics without being necessarily just lost in the woods. So Beth, next slide, please.
Sorry. I was trying to get rid of those lines that showed up, and I think I have not advancing for some reason. Okay. There we go. Okay. All right. Sorry about that. Okay. Thanks, Andy. Ashley, if you can get rid of those red lines on there, that'd be great, because I'm going to be talking and I won't be able to figure that out. So we wanted to talk a little bit about the teaching modules themselves and the methods that the different modules have. There are 4 near surface geophysics modules, which are in the Iguana sub collection, and that is ground penetrating radar. So and these are all ways to look at the near surface and be like, what's down there? Because I can't get there myself. And so this case, it's radio waves that reflect off of targets below. There's electrical resistivity, which is direct electric current applied to the subsurface. And then you can see different places with different amounts of electricity transit. seismic refraction, so sound waves that bend at interfaces and allow us to say things about some of the different properties down below, and also magnetics and gravity. So using these fields to measure contrast and physical properties below. So all of these have prepared data sets and case studies that I will mention, but in particular, these three have lone instruments available. So GPR, resistivity, and seismic refraction. And I'll say that in magnetics, their phones are an aspect, you know, the magnetometers in phones can also be used there. The GETSI field modules have two main modules, one of which has two methods in it. So there's global positioning, which is satellite signals to determine location, structure from motion, which is using photogrammetry to produce high resolution topographic data. And nowadays less commonly used, but still featured in the teaching resources, is another way to do high resolution topography, which is terrestrial laser scanning. And again, we have instruments and or supplies available for both the GPS processing, or sorry, surveying, and the structure for motion. We do for TLS as well, the terrestrial laser scanning, but it's a bit more complex. So we don't focus on it as much. So now we're going to go through a quick overview of each of the different teaching modules. And this first one, I'll sort of highlight some of the characteristics that they each have. So so all of these were done in a rigorous development and testing process, using multiple authors at different types of institutions to get a broad range of what different types of students might need. They all have clear learning goals at both the module and the unit levels, such as design and conduct the surveys, be able to say the societal impetus for why you would do it, and if appropriate, compare and contrast different methods. They're all designed for flexibility as well. And so that means there's a bunch of different applications that are featured potentially, or other ways to tailor it for what makes sense to your particular site. You do not need to use the whole thing. Subsets work great. So in this particular case, there's an introduction to terrestrial laser scanning or structure for motion, depending on which one you might like to use. There's a bunch of different applications, and there's guidance on how you would assess the project. Within the structure from motion method, this is the idea of you move the camera, like where you take pictures, but you have overlapping between the different images, and that helps you to build a 3D model called a point cloud, which is pretty much like this sort of thing that our two different eyes do, and then they're in different places, and then we can make a 3D model in our brain. This can be done from a variety of platforms. A lot of people are familiar with drones or UAVs, but it can also be handheld or on a stick. Handheld works really well for intro level students, or people getting started. Balloons and kites can also be done, and this brings in the point clouds, which can be then turned into a variety of topographic data sets: shaded, relief, photorealistic, things like that. And this can be used for hazard analysis. It can, so the last one I featured, here's some like a fault scarp, like that's gorgeous, right? Other faults and geomorphic features on this one. This is a lobe of a landslide, which you can, get the volume of it. You can do change detection. This is showing change detection after a flood where the thaw wagged, moved and deepened. You can also use it for things like geoengineering, so road cut design, and looking, using the geometry to determine maybe how you would best do your road cut based on the joints and fractures, or things like seismic trenching and archaeology and things like that. So there's a wide array of things you can use point clouds with. The other geodetic focused module, so this is a high precision positioning, mostly with the kinematic side GPS. And so again, it starts out with the GPS introduction to the method and the motivation. And this is pretty much true for any type of GPS. And it moves on into a variety of different survey methods. Again, the unit 2 and the 2.1 and 2.2 are most likely to be the ones that people engage with. and that is the getting out there potentially with the instruments and collecting for different purposes. So what are those how does this work more exactly? The GPS works by having 4 or more satellites that and it's the time delay between the satellite and when it is received by a phone, by a survey instrument, by a high grade permanent station. And it is these 4 satellite signals, but really it's better to have more than 6, enable you to solve for the 4 variables, which would be your XYZ position and time, because your clock's not quite as good. Again, the kinematic surveying that is often done at the undergraduate level is in increasing the accuracy of what you know in the moving around, we call it a rover, by getting corrections from a nearby base station that definitely knows where it is. And so this allows you to move from meter scale of knowing where you are, so to speak, to centimeter scale. So really helpful in a wide variety of applications. And so you can use things like creating topographic data. I mean, we talked about that in the last one, but you can also do it with GPS. You can have somebody run all over with a backpack with a antenna on their back and use something like GIS to turn that into a map of that feature. You can also do change detection with this, much like you can do with the point clouds. For instance, this is showing the map of a bunch of different points on a creeping landslide, and they go and revisit it with the class periodically, and they can see where the motion is occurring on this slump in Idaho. And of course, GPS is just simply great if you're like, I care about seismic and I would like to know where all my nodes are or where other parts of my survey are. So the GPRs come with GPSs on them, or you may be geo-referencing your point cloud from a structure from motion survey. So simply using this for geo-referencing other things, also super valuable. All right, and back to seismology with Andy.
So the seismic unit of Iguana, seismic module of Iguana has 3 units. The first is kind of a motivation where we introduce shallow seismology and sort of explain how it fits into the context of geoscience and environmental problems, and kind of hopefully convince students why they would want to get excited about this. The second unit is kind of the core physical background. This is where we go into the actual Snell's law that drives seismic refraction and talk about how seismic waves travel in the ground. And the third unit is hopefully the most exciting. This is where we have a case study example that uses real data, and we give instructions on how to collect your own data at your own institution if you are using these instrumentation. Next slide, Beth. So a little bit about how the seismic method works. The whole idea here is that sound waves travel at different speeds in various geologic materials. So for example, in soil, the sound waves will travel slower than in the rock underlying the soil. So if we use a sound source, which is often a sledgehammer struck on the ground, that energy is going to propagate outwards from that source, and some of it's going to go downwards where it interacts with the faster velocity materials like bedrock. Because the sound waves are traveling at the velocity of that faster material at depth, as they move across the array of sensors, at some point, the waves that are traveling at the faster velocity outpace those that are traveling at the soil velocity. So for example, the ones in the red arrows in this diagram will start to arrive at the geophones sooner than the direct waves in the green arrow. And that ends up making a plot looking like the graph on the right side of the screen here, where you see that there's 2 different slopes. The one with the green dots is the slope of the arrivals as a function of distance over time for the soil, and then the red slope is a different slope because it's related to the distance over time experienced by waves traveling at the faster velocity. And so the whole point of seismic refraction data analysis is to figure out the depth to that faster layer and the velocities of the top layer and the lower layer, and use that to interpret things like how deep is the bedrock, or where is the water table, or what are the material properties of the different materials that can be used for geologic interpretation, geophysical experiments, or environmental studies. Next slide, please. So some examples of applications. Things like infrastructure planning. So if we're going to dig for a foundation, when are we going to actually run into the bedrock? How expensive is it going to be to do the excavation? For water resources, we can interpret things like the top of the water table or potentially even the porosity of an aquifer. For environmental remediation, we'll use some of the same themes that are relevant to water resources, but then we can actually use that to parameterize models that might influence our understanding of where contaminants flow in the subsurface. And then things like geohazards, so using seismic analysis to predict where landslides might be more likely. So that's kind of a summary of the seismic applications.
Awesome, thanks. And now we'll hear from Sarah on some of the other methods.
So the ground penetrating radar, or GPR module, has 3 units. The first one is just an introduction to the method. The second one lets students actually do some basic processing of GPR data using an app. And then third one gets into a little bit more about where and when GPR works and doesn't. If you have conductive soil, the radar wave gets absorbed and you won't see very deep. So there are places it doesn't work very well. And the other issue can be that multiple objects can appear similar. A grave, a tree root, a buried pipe may all look similar in a single GPR profile. And we've added material recently on how to collect your own data. So next slide, Beth. Okay, so how does this method work? So in the picture on the left, you see this cart with this yellow box at the bottom of it. The yellow box contains a transmitting antenna and a receiving antenna. The transmitter emits an electromagnetic pulse and the receiver records an electromagnetic pulse. And then you push this cart around the ground and you see what in the ground is reflecting the radar waves. So the little animation on the right is going to show an example of pushing a cart over an environment where you have a dipping contact. And think of that little black box as the yellow cart. A pulse is emitted, it reflects off that boundary, comes back to the cart. The lower diagram shows what is recorded by the system. So the travel time of the wave is plotted on the vertical axis with positive time down, because the longer it takes, the deeper, the farther away that reflecting horizon is. So you can see by the end of this, Beth, maybe you can forward it to near the end, that when you're done,
Sorry, that was
you
weird.
have,
there we go.
We have like apparently a dipping layer that is just like the subsurface, but somewhat distorted. So Beth, I'm ready for the next one. So what can you use GPR for? So some examples are looking at layers in the ground associated with interesting things like sinkholes or volcanoes. Next slide. GPR can also be used to image tree roots. If you look at the picture in the upper left, the upside down U's are each the result of pushing the radar over a tree root. Graves shown in the lower left produce sort of similar like responses. So these are each of these upside down U's is the return from a casket. Next slide, Beth. And finally, even if you're in one of those environments with conductive soils where the radar may not work very well in the ground, it will always work for engineering kinds of applications. For looking for buried utilities, this is a very common application, and for evaluating reinforced concrete, because the radar is sensitive to where the rebar is in concrete. So you can always do a survey on a concrete floor, say of a multi-story building, and learn where the rebar is. These latter two are a source of common employment for people who know how to use GPR. Next slide. Oh, onto the resistivity module. So the resistivity module has 5 parts. The first and the last are really focused on data acquisition and interpreting the data. And the intermediate 3 go into at a higher level aspects of processing GPR data. Next slide. So how does the resistivity method work? Well, we begin with 4 metal stakes, which we call electrodes, put into the ground. And next slide, or next thing, Beth. So we have an instrument that drives current between two of the electrodes. So in the example shown, current is injected into the ground at the rightmost electrode and extracted from the ground at the leftmost electrode. And then the voltage difference between two other electrodes is measured while that current is flowing. And with that measurement, you can determine how much resistance the ground is applying to the current that's flowing through the ground. And from this resistance, we can get information about the resistivity, the material property of the ground. So in modern systems, we actually don't just put 4 electrodes out, we put a whole line of electrodes out, and they're all wired up to the control box. Next slide. So how does this work? So for example, if you put out a bunch of electrodes, the box will say, okay, let's drive current between the first and fourth electrode. And this gives you sort of an average and apparent resistivity of the patch of ground where that current has flowed. Then the box will say, maybe let's drive current between the fifth and the eighth electrode, and you get a different apparent resistivity value for that part in the ground. Next, click. Okay, great. And then if you talk to electrodes that are far apart from each other, send current between them, that drives current much more deeply, and then you can sample the resistivity at greater depth. So each of these things is one measurement, and the final step is to take all of those data points and put them through a computer program that does what's called an inversion, and out comes a cross-section, a two-dimensional profile of the resistivity of the ground beneath your electrodes. So reds would be areas of higher resistivity, blues areas of lower resistivity. Okay, so some applications of the resistivity method: it can be used in wetlands to try to determine the structure of the shallow layers in wetlands. That's an example shown on the top. The middle example picture on the left is of imaging the freshwater saltwater interface at a coastline, where yellows are fresh, blues are saltwater. And then finally, it's also good for mapping the water table. The bottom image shows an example where the reds represent dry sands and the yellows are saturated sands. So
Oh, whoops, sorry.
yeah, no, this is fine. On to
Okay.
the gravity and magnetic unit. This is broken out into 3 parts. The first part is an introduction to the gravity method. The second part, an introduction to using measurements of the magnetic field for shallow and environmental problems. And the third is some field data and some practical exercises. So the first 2 actually are worked around videos, which I think are great. Anyway, next slide. Okay, so how does the gravity method work? So you can imagine you have a very sensitive spring, and in the upper left we show a hypothetical spring held over that's supposed to be an ore body, and the ore body is denser than the surrounding rock, so it actually exerts extra gravitational attraction on that spring, and the spring stretches a little bit. Now if you move the spring over the tunnel, it's less stretched because the tunnel is actually a void. We're missing mass there. So there's lower gravitational attraction. So in the photograph on the right shows one of these boxes with these incredibly sensitive springs inside. You have to settle it down. Taking a reading takes a little bit. And this photo also shows a GPS, which is important because you need to know the elevation of your measurement. The farther away you go from the center of the Earth, the weaker gravity is. Next slide, Beth. Okay, so how does magnetics work? Well, basically, you have a sensor that measures the strength of the Earth's field at the location of the sensor. And in this photograph on the left, the woman in the center, the white sensor over her, I guess it's her left shoulder, is what measures the magnetic field. And unlike gravity, this can be measured very quickly. You can collect thousands of data points in a day. And you'll notice that the woman on the right is holding a compass because she's going to lead the woman with the magnetometer to try to walk in a straight line. And they are over a lava flow, which is usually a good source of a magnetic signal. Yeah, so on the right is from the magnetics video. You don't necessarily need a base station to collect data, but it can be useful if you're looking for small magnetized objects. Oh, I should have said, what do you detect with magnetics? You detect objects in the ground that are magnetized. So metal objects that have an induced magnetization, or igneous rocks that have a remnant magnetization. Okay, next slide. So what can we do with these methods? Well, there's a whole bunch of different things you can do with gravity on large and small scales with time lapse, but on campus, there's something really fun you can do that's relatively easy with students. And that is take your gravity meter and take it in a multi-story building and measure the gravity on different floors. And you can actually detect the reduction in gravity, the gravitational attraction, as you go farther away from the center of the Earth. And magnetic applications, metal things in the ground, abandoned wells, this is really important today, storage tanks, UXOs, and archaeological things, buried infrastructure, and again, igneous rocks. So I think that's it, Beth, for those. Yeah.
Yep. So before we give you some time to actually look at some of the resources yourself, I did just want to go over, so you can also look at this, while you have a little bit of free time, how to access equipment and instrumentation. So EarthScope Consortium, which again runs the geophysical facilities for the National Science Foundation, has a variety of instruments available. Oops, and the page there, and I will also, I dropped it in the chat twice now, sort of the 3 relevant links to the resources, but this is our geophysics field education page. And so we have the GPS and the multi-channel seismic refraction instruments, ground penetrating radar, also some supporting supplies for the structure from motion. And then here in the center is how you go about requesting it. And this is the same portal that takes people in who are maybe doing a big, project of seismic in Greenland or something like that, or in the Himalayas. And so in the purple text here, I've gone through the specific guidance how to fill out this request form for education, so that some of the less obvious answers, you can just look at the bullet points and just fill it in pretty quickly. The cost is just shipping. For the primary instruments here, it's there's no rental cost at all from EarthScope. And so what we do have some typical pricing here that it costs to ship these instruments back and forth. We do also have a fund for low resource institutions such as community colleges, where we can waive your shipping fee and cover that out of our educational budget. Andy is also at the University of Wyoming, which has additional instruments. And so we do also have some funding to cover the renting for you of electrical resistivity instruments. And we will be acquiring at least one of those ourselves from EarthScope. And so if you're interested in that route, I suggest you email me, and we can work through the checklist process together for that. All of this is first come, first serve. So when you know your dates, I recommend you go ahead and get something in. Or even if you're not 100% sure, it's easier to tweak it 1 week than to have it land kind of last minute. There's a series of other tabs here that I'll just also point out. So there's teaching resources. This just points to the modules that you've heard about. There's a tab where I've pulled out the actually sort of instrument and software guides all in one place. These are all in the modules as well, but sometimes you're like, where's the geode one for the seismic stuff? And so that's called out. Where links to how to learn about workshops and stuff like in-person and other events. So what I would like to do at this point is give you all about 7 minutes or so. I mean, you can take, basically between now and the end of the hour, we have for you to explore and learn what you need to know more what you would take away from this. We suggest that you consider jotting down your thoughts on which methods are you interested in, what instruments are which specifically instruments would you want to borrow, or maybe you have some already and you wouldn't need to borrow all of them. What questions might you address in your course? And then what questions do you have for us? So at this point, if you check in the chat, I've put the links to the teaching resources and also to that sort of instrument request page. And we're going to kind of stop talking for like 7 minutes or so now and give you a chance to actually explore. After that, you can keep exploring, but we'll open it up for people to sort of unmute and ask questions that are harder to put into the chat. You can also just put stuff into the chat. We will be monitoring that. So go forth. You're probably looking, Sarah and Andy, but there's a question about borehole stuff, which I can't answer. I don't know if you have suggestions for Amelia in the chat there. Somebody just joined, so I re-put the links in that people are exploring right now. I'm going to say we have about a minute left of sort of the quiet exploration time, and then I'll start more talking. All right. People should feel free to keep looking through the resources, but I think we've reached about 7 minutes now, so some of the questions are a little easier to answer verbally. So I might work my way back a little, and then this is also a great time to raise your hand and ask, and we can call on you, and you can unmute and ask things that are more complicated, or suggestions or input or anything like that. So I think I'll just say a little bit more. Thank you, Sonia, for prompting us. There was questions like, where are these instruments anyhow? Which is totally reasonable. The EarthScope Primary Instrument Center, which has the acronym EPIC, is at New Mexico Tech in Socorro, New Mexico. And that is where everything is shipped in and out of. There is potentially the opportunity to come there and try things out. And there is also, although that's, yeah. So if that's something you think you could arrange, talk to me and we'll see. It's more typically done with research groups that have NSF funding, but I would, be up for trying to arrange that if that was a place that you could come. We also are working to we have had a number of workshops in person, and we are hoping to have another one next year, and maybe also do some virtual options where we could send instruments out and then sort of help people scaffold through it with live on, with in-person cohort opportunities. So let's see, I think there was a question. Also, I saw something about, is there a module and resources that combine the structure from motion and the georeferencing? In general, we maybe I'll say it's in production and has been for several years. So not yet, but I would say basically once you do the first 2 units in the GPS, you know how to use the GPS and you can use it for whatever you want. And it becomes pretty straightforward to see how that would be used for the other methods. And I'm always available, to talk about it more. That is a place where I would like to have maybe a mini unit where I'm like, so you need GPS for georeferencing of other things and address it more directly. Am I missing any other questions that I should be? If we have our own equipment but have technical questions, yes, you can. So if you look at I can put this into the chat as well. education@earthscope.org. This email, I mean, you can always write to me, but I could be on PTO or something, you know, or busy running a workshop. So this is an email group that goes to 5 of us in the education group, and we would point you towards if we had our own knowledge, we would try to answer you, or we point you to instrumentation folks that could help. And yes, thank you, Sharon, Sharon, for saying that there is a field course, a remote field course that Sharon did during COVID that brings things together. And so that is a resource online that has, thank you for pointing that out. So that sort of featured how she did it in the virtual setting, but obviously that can be translated easily into what you would do live as well. The and that, I'll just give a plug for that. That's got some great like river assessment, you know, activities, and also includes some terrestrial laser scanning data as well. So all 3 methods are brought together in that 2-week course. Does anybody want to raise their hands and ask any question that's a little complicated to put in the chat? All right, Sarah or Andy, can you tell any questions that we've missed? It's been quite a vigorous list so far. If anyone we've missed your question, you can just unmute and ask it. Could you address the difficulty in using different types of instruments? For instance, typically some instruments are more persnickety, lovely word, and others may require more time and measurement to get the data that will be seen as rewarding for students. That is a great question. May I turn that over first to Sarah? And then Andy, if you have anything to add to it, like if you were like, what should I pick for my intro students at Highline College that will be least confounding?
Well, I'll jump in. The ground penetrating radar is nice because you see the data in real time, like the little animation showed. So that can be very satisfying. And yeah, it's a relatively robust system. So, I mean, these things are made by commercial companies for operators that understand less about, don't understand much about radar. And so the instructions are fairly straightforward too. I think a GPR is low hanging fruit.
I think that's reasonable feedback from our like in-person workshops as well. Is we don't tend to hear people saying things like, I don't think I could do this with my intro students. Some of the other methods would be a bigger ramp up potentially. And maybe I'll just, because I love GPS, I'll be like, and there's a GPS unit on your GPR. So once they get the acronym straight, you can at least give them an introduction to the GPS, even if you don't decide to also get a base station, right? So if you're just running your little GPR cart around with the rover on top of it, it'll have like couple meter accuracy, which is generally enough in most cases. But if you wanted to additionally bring in the GPS, you could order a base station and have them learn about the base station rover combo. And then you would really for sure know where your GPR is at all times. GPS is also one that's definitely been done at the intro level. And honestly, structure for motion has been done by 2 community college instructors that I've been part of. And they work really well on campus as long as you just stay not under trees. Somebody says, we have shallow targets buried at our field research site. This was done way before I got here. GPR the best? Well, certainly GPR would give you could run over and see if we could find them, you know, right? Targets are small. I mean, what would you say, Andy? Like seismic is really more for like, where's my bedrock, which is also cool, right? Because lots of places have bedrock within 20 meters, you know.
And you can use the magnetometer like a big scale metal detector. So if they're metal buried objects, the magnetometer is a good way to look.
And you know, even if you don't have buried targets, like there are, as you know, what would you say, as Sarah was mentioning, like infrastructure underground, like all over campuses, right? You know, so just simply being like, does the light post, you know, does this one to this one have a connection between them, or is the electricity coming in from somewhere else? You know, I mean, like just a little bit of mapping of like where that stuff might be buried could be pretty interesting and attainable within 100 feet of a given building. Okay, where are we for time? Oh, we are pretty much at the moment. Let me stop sharing and give our last minute over to NAGT.
Great, thank you. I'll go ahead and share my screen again. Please cooperate soon. Okay, there we go. Yes, let's go ahead and wrap up for today. Thank you all for joining us, and thank you to our presenters for a wonderful webinar. If you'd like a certificate of attendance for participating today, please complete the evaluation survey, and that will pop up a link to the certificate form. I'll drop that in the chat now for everyone. One moment, please. There we are. You'll be able to find resources mentioned today and the recording from today's webinar on the webinar page. Just please hold tight for a few days while the recording is processed. We send out the video for captioning, so it just takes a little bit. Also, please join us for our next webinar on Monday, October 21st, which is Teaching with Investigation and Design in the Undergraduate Science Classroom. If you're not registered for that, go register now. And finally, on my slide here, there's a link to the webinar series homepage where you can find the webinar schedule, the archive of all the past webinars, and information about our sponsoring projects and programs. That's all I have.
Awesome. Thank you, everybody.